Hello, my name is Jenna Okwara, and today I'll be presenting on my work on contract-driven test generation. To begin, let's start with the motivation and goal. So a contract is a set of agreements or specifications that define the expected behavior and responsibilities of software components, functions, or objects. For the scope of my project, I focused on the precondition, postcondition, and invariant aspect. The goal of this project was to develop a system that analyzes and verifies code contracts by generating and evaluating test cases. Now, to briefly move on to a related work section and background, I performed three brief literature reviews. The first review was on contract-driven development via CCD or CDD. This research reduced the amount of burden of writing unit tests, leveraging processes programmers already utilized during the development stages. Ultimately, they were able to automate the extraction of test cases from failure-producing runs. Please refer to architecture on the right side of the screen for more reference. The next paper I will be reviewing briefly concerns the automatic test case generation from formal contracts, specifically Spark formal contracts as an input that bridges the gap between formal proof writing and software testing. The goal of this research was to automatically generate test cases from contracts. The last piece of literature I'll be reviewing was on data analysis workflows. And ultimately, the researchers were looking on how to enhance robustness and portability of workflows via data analysis, via also a scope focused on contract-driven design. Now, for my proposed architecture, please refer to the legend on the left side of the screen for any reference throughout my presentation. I begin with an input that contains contract specifications and sample contract from data sets. I feed this into a contract parser and then a constraint extractor. Finally, I'm able to move it down to a test case generator where I find the optimal min and max using Rosette Solver to generate test cases within the minimal min and max test input that also passes through the preconditions. Now I feed this into the postcondition verifier, which checks that if these given tests that satisfy the preconditions within those bounds also satisfy the postconditions. I lastly then output this via generated test cases and a final report. Moving on to my approach, I utilized Rosette due to three reasons. Its contract parser development, constraint extraction and implementation, and test case generator. Rosette supports preconditions, postconditions, and invariants, and creates abstract syntax SAT representation. It also handles different types of assertions and allows for tests to be generated via Rosette Solver. I also utilize ChatGPT for contract understanding and generation, which you will see later in the presentation, and also test case enhancement and debugging and analysis. Lastly, I also utilize version control via Git for tracking implementation progress. For the evaluation framework, I utilized ChatGPT to generate pre- and post-conditions. I broke it into three suites: initial evaluation suite, which ranges in difficulty, choose best suite that consists of varying conditions, and LeetCode suite consisting of LeetCode style questions. The recorded evaluation metrics are to the bottom left of the screen, and I focus mainly on the three listed at the top: grants coverage, the generated tests, pass rate, and number of contract violations found. Moving on to my implementation, it can be broken up to 6 stages, but I'll briefly go over each one. So I begin with contract analysis, which extracts explicit constraints from the code contract definitions, and also identifies the implicit constraints within the code itself. I then move on to the test strategy generation within boundary conditions and edge cases, prioritizing paths that likely reveal contract violations. Feed this into a constraint solver via SMT and Z3. And then I move on to the test case construction, which generates executable test code from the constraint solutions. I then introduce the post conditions, defining expected outcomes, and also inserting meaningful post-condition coverage. And lastly, have a pre- and post-condition verification, making sure that both the pre- and post-conditions are satisfied with the input. For the results, I'll start with the initial suite, as I mentioned before. So the necessary suite includes different contracts, pre and post conditions, test bounds, and number of cases that vary. However, for this example, let's focus at the very top function body highlighted in orange. If you look to the right, you will see its output. Its output consists of the inputs via each test and also the pass rates. To the very top, you see pass cases and total cases. For this example, 5 out of 5 of the cases passed, given the input values for X and Y. The next suite is called the choose best suite. What's really interesting with this is that all the function bodies are the same, as well as the min and max values, and also the number of cases. The only thing changing in this example are the pre and post conditions. The purpose of this experiment is to see how the pre and post conditions impact the pass rate. As you can see, the bottom program performed the worst, while the middle program performed the best. Why this may occur may be due to pre and post conditions being either too tight or too loose in the very bottom function, resulting in a pass rate of 40%. To be optimal, a programmer may aim for pre or post conditions that are most similar to the center function, as that is most appropriate for the function body being defined. For the last suite, it's called a LeetCode suite. It's very similar to the initial suite, except all the function bodies within the suite is focused on LeetCode style questions. Then this is tailored more to intro computer science students or intro computer science learners. Not only could they use this tool to validate their pre and post conditions, but they can also see and observe the relationship between pre and post conditions as well, observing which pre and post conditions are appropriate for a given function and how they interact via bounds and number of cases as well. To conclude, my tool supports the automation of pre and post conditions, the exploration of value ranges, utilization of results min and max function, and custom boundary inputs. In the future, I'd love to extend my work to cover more complex data structures and more advanced functions as well.